আসসালামু আলাইকুম প্রিয় শিক্ষার্থীবৃন্দ, আমরা গতদিন বলেছিলাম যে আজ 8টার সময় স্যারকে নিয়ে আবার নবম শ্রেণীর সেট নিয়ে আলোচনা করব। তো আমাদের প্রায় 1 ঘন্টা লেট হয়ে গিয়েছে, আসলে একটু ভুল বোঝাবুঝির কারণে লেটটা হয়েছে। আন্তরিকভাবে ক্ষমা প্রার্থনা করে আমরা আজকের ক্লাসে যাচ্ছি। তো সেট সম্পর্কিত আলোচনার পূর্বে আমরা একটু জানতে চাই তোমার কাছে, সেটা হচ্ছে যে জিরোকে আমরা কি বলবো? এটা কি জোড় বলবো না বিজোড় বলবো? আমরা সাধারণত জানি 1, 3, 5 এগুলোকে আমরা বিজোড় বলি, পাশাপাশি আমরা 2, 4, 6 এই জাতীয় গুলাকে আমরা জোড় সংখ্যা বলি। বাট জিরো কি আসলে জোড় না বিজোড়, এটা নিয়ে কিন্তু শিক্ষার্থীদের মাঝে কিন্তু একটু কনফিউশনের ভিতরে আছি আমরা, যে এটা জোড় না বিজোড় হবে এটা তারা জানতে চায়। তো এইটা সম্পর্কে যদি একটু বর্ণনা দাও সেটা ভালো হয়, তারপরে আমরা একটু পরিচয়টা আবার একটু জেনে নিতে চাই।
My name is Samuel Ali Masad and I read in Kaliganj Quality English Version School. I read in class 5.
তো আমরা স্টার্ট করতে পারি, ওকে?
So, the proof begins with how an even number is defined.
Yes.
Now, we are going to use a bit of set theory here. So let's say E. E is the set. We're going to use another different type of writing sets. We're going to discuss that in the video. E contains elements X, where X is an even number. X is an even number. Okay. So, what we want to prove is 0 is a part of this set. Now, for X to be an even number, X over 2 must belong to the integers. That is the condition for an even number. So, this must mean that X over 2 equals N, where N belongs to the integers. Here, if we use this equation, X over 2 equals N, and multiply by 2 on both sides, these cancel, we get X equals 2N. So, and we already have established that X is an even number. So, this is the form of an even number. This is an even number, okay? So, but now what we do is, what about X equals 0? Because if N belongs to the integers, then we could prove that 0 is an even number. So, 0 equals 2N. Let's divide both sides by 2. We get 0 over 2 equals N. 0 over 2 is just 0, which means N equals 0. Now, 0 it does belong to the integers, okay? So, we have officially proved that 0 is an even number. But if you think that proof is wrong, I can explain otherwise. This is proof by contradiction. Proof by contradiction. So, let's say 0 is not an even number. So, what can it be? What is the form of an odd number? An odd number, you see, let's just write out some numbers. 0, 1, 2, 3, 4, 5. So, let's say 3. 3. An odd number is always one more than an even number. For example, 5. 5 is one more than an even number, 4. So we can just say this as 2n plus 1, right? This is a form of an odd number, which means 0 should be an odd number according to this. But if we subtract both sides by 1, we get -1 equals 2n. We divide by 2, we get -1 over 2 equals n. Now, -1 over 2 is just -1/2. That obviously does not belong in the integers. So, contradiction. Which means the opposite must be true, and the opposite is 0 is an even number, which is 2n. And that's how we prove that 0 is even.
ওকে, শিক্ষার্থী কিন্তু আমি একটু যেটা একটু শেয়ার করি সাথে সাথে বাংলায় একটু শেয়ার করি। আমার মনে হয় এইটা যদি আমরা এমন ধরি 0 1 2 3 4 ডট ডট ডট, তো আমরা যদি 0 ধরি যে এটা হচ্ছে একটা জোড় নাম্বার। ওকে,
it is an even number.
আমরা ধরে নিই যে 3 হচ্ছে একটি জোড় সংখ্যা, তাহলে 3কে আমরা জোড় সংখ্যা ধরে নিলাম। হ্যাঁ, তো 3কে যদি আমরা জোড় সংখ্যা ধরে নিই তাহলে অবশ্যই জোড় সংখ্যা তো 2 দ্বারা বিভাজ্য হয়। ওকে, তো আমরা 3কে যদি 2 দিয়ে ভাগ দিই তাহলে কত দাঁড়ায় এখানে 1.5, বাট 1.5 কিন্তু ডাজ নট বিলংস টু জেড, অর্থাৎ পূর্ণ সংখ্যা হয় না। তাহলে 3কে আমরা জোড় ধরে নিলাম, তাকে 2 দিয়ে ভাগ করলে যে সংখ্যাটি আসবে সেটা পূর্ণ সংখ্যা হতে হবে এবং নিঃশেষে বিভাজ্য যেটা হতে হবে, তাই তো? কিন্তু সেটা আমরা দেখলাম কি 1.5 আসলো, যেটা জেড এর ভিতরে নাই, সুতরাং এটা জোড় সংখ্যা হতে পারে না। বাট আমার ধারণা আমি বুঝলাম কিনা, আর যদি এমন হয় যেমন 4 0 একটি জোড় সংখ্যা, সে আমরা 0 তো জোড় সংখ্যাই, তারপর 0 যদি জোড় সংখ্যা হয় তাহলে 2 দিয়ে ভাগ যাবে, ভাগ গেলে রেজাল্ট আসলো কত 2 0। তাহলে এই 0 আমরা দেখবো যে জেড এর ভিতরে আছে কিনা। অবশ্যই জেড এর ভিতরে আছে, এমন কিনা।
It has no decimal part.
ওকে, তাহলে 0 যেহেতু জেড এর ভিতরে আছে, অর্থাৎ ইন্টিজারের ভিতরে আছে, সুতরাং আমাদের এই লটা ফলো করছে, তাই তো? জোড়ের যে 12 এই ফর্মুলাটা ফলো করছে, সুতরাং আমরা 0 কে বলতে পারি কি ইভেন নাম্বার। আর 3 কেন ইভেন নাম্বার না? যেহেতু এটাকে 2 দিয়ে ভাগ করার পরে 1.5 পেয়েছি, অর্থাৎ ডেসিমাল নাম্বার আছে এবং এটা জেড ইন্টিজারের ভিতরে নাই, সো এটা 3কে আমরা ইভেন নাম্বার ধরে নিল। আসলে এটা ইভেন নাম্বার না, অর্থাৎ জোড় নাম্বার না। আর জোড় যদি না হয় তাহলে এটা বিজোড়। বিষয়টা তেমন, ঠিক আছে? ওকে, থ্যাংক ইউ। তো আমরা এবার সেটে চলে যাই। আমরা সেটে আজকে আলোচনা কতটুকু করা যায়?
Actually, I want to discuss this notation right here.
ওকে, হ্যাঁ, আমি দেখেছি, তো আমার মনে হলো যে বাংলায় যদি আমরা এভাবে একটু সহজ করে দিই তাহলে সুন্দর হয়। তো ঠিক আছে, তোমার আলোচনা কন্টিনিউ করো, আমি মাঝে মধ্যে আসবো। তো শুরু করো। আমরা শুরু করতে চাই এখান থেকে। সেটের আজকে কোন অংশটা আলোচনা করব? সার্বিক সেট থেকে, সসীম সেট, অসীম সেট, তারপরে আমরা আমরা কোথা থেকে শুরু করব? এখান থেকে শুরু করি। হ্যাঁ, সেট প্রকাশক পদ্ধতি আমরা গতদিন আলোচনা করেছি। আজকে হবে সেটের যে বিভিন্ন পদ্ধতিগুলো আছে, অর্থাৎ তালিকা পদ্ধতি, সেট গঠন পদ্ধতি, এগুলো নিয়ে আমরা আলোচনা করব।
So a set is a collection of things. Just a quick recap. So there is 2 ways, well actually there's 3 ways to represent sets.
একটু বড় করে লিখি, অক্ষরটা একটু বড় করে লিখি, স্পষ্ট দেখা যাবে।
So the first way is the roster method. It's also called the tabular method. I like calling it the roster method because it sounds cool. And the other one is the set builder method. This method is much more complex, but it is much better at representing sets. And the other method is the Venn diagram. The Venn diagram. Now this is, a visual way. Like if you're a visual learner, this will probably help you a lot. The Venn diagram. Although I do recommend the set builder method. This is probably the best one. This is probably the second best, and this is probably the worst. So first we're going to start with the absolute simplest one, the roster method. So for example, let's actually consider the set from before. Let E be the set of all even numbers. So E starts from negative infinity and stuff. And then we get into bigger numbers. For example, -4, -2, well, to be honest, not negative, plus or minus 0. Plus or minus 0 really does not matter. So yeah, and 2, 4, 6, ... Actually, you know what? I'm gonna remove the plus or minus right here. Yeah, removed. Okay, cool. So this would be the roster method. This is a roster method. Because, we just write the elements out. Now let's see the set builder method. Set builder, probably the best one. This we will write like this. This is how we will write it. Actually, there is actually many ways of writing this exact thing. So, this is how you write this set. This is much more simpler, but it takes up much more space. This is much more complex, but it takes up less space. We can actually explain something right here. This has an infinite amount of elements. So this, we would consider an infinite set. This is also an infinite set, actually. It may not seem infinite, there's no dots at the end, but this is still an infinite set.
ওকে, তো আমি একটু বলি বিষয়টা এমন কিনা। আমরা দেখলাম এখানে প্রথমে হচ্ছে কি, এটা হচ্ছে তালিকা পদ্ধতি, আমরা বাংলায় বলি যেটা রোস্টার মেথড। ওকে, তো এটা হচ্ছে একটা জোড় সংখ্যার সেট, ইভেন নাম্বার সেট। তো এই ইভেন নাম্বার সেট আমরা কেন বলছি, জিরো আমরা একটু আগে দেখিয়েছি, জিরো হচ্ছে ইভেন নাম্বার, এবং বাম হচ্ছে নেগেটিভ ইভেন নাম্বার, এবং ডানে হচ্ছে পজিটিভ ইভেন নাম্বার। আর যেহেতু দুই পাশে ডট 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 আছে, অর্থাৎ চলমান, তাই তো, অর্থাৎ এই সেটের উপাদানগুলো গণনা করে শেষ করা যাচ্ছে না, সুতরাং এটা হচ্ছে অসীম সেট বা ইনফাইনাইট সেট। ওকে,
It's not infinite, it's infinite. Okay.
Okay.
Cool. This is the more advanced set builder. Builder method. Here it says it is x. This will be read as for all x. Yeah, this is for all x. This should be read as for all x. This colon always means such that x equals 2n. Obviously, that's what we said earlier. That is the definition of an even number. And n should be part of the integers. N belongs to the integers, which is z. So this is what it says. And comma always means and. Just take that. So this is also an infinite set because there are infinite numbers which satisfy these conditions. Yeah, you can.
ওকে, দেন এখন আছে আমাদের সসীম সেট, যেটা ফাইনাইট সেট।
Finite set.
Okay.
Finite sets have a finite amount of, elements. Now, one thing I want to talk about really quick is, let's say z. Z is the set of all integers, so it is x such that, now this is actually really complex here, x plus negative. I know, why do we have to do this? Plus negative. This is because of something called Riemann-Frankel set theory, which is much more advanced. And then we have the floor of x. This equals 0. So basically the floor function here is just removing any decimal part. For example, 4.58. Inside the floor function, the decimal part's gone, it's 4. So if you put 4 in this function, we just get 4. So it's just x minus x equals 0, that's it. So this is the set of integers. Now we take the set of all even numbers from before. So let's say that set is E. So x equals 2n, n belongs to the integers. So now this the thing I want to say is the amount of elements in these, sets are both the same. They're both infinity. This has infinite sets, this has infinite sets. But when you actually write it out, it seems like it's not, right? Because, there are still the odd numbers, so it seems like it's this. The even numbers are just half of the whole integers. But here's what I want to talk about. These are called equivalent sets. Sets that have the same amount of, elements. We can prove that two sets are equivalent by something called a one-to-one correspondence. If we can match up every single element of one set to every single element of another set, then those sets are equivalent. So here we can match up 0 to 0, we can match up 1 to 2, we can match up 4 to 2, 2 to 1, and we can match up 4 to 2, we can match up 6 to 3, match up 8 to 4. We can actually do this for every single number, which proves that these are indeed equivalent. That's what I want to talk about. So now with the rest of this thing, we have the Venn diagram. Now, the Venn diagram in this, book, it's actually discussed like at the end of this chapter, but I'm bringing it to the beginning because it's actually very important. So like, for example, let's just have an example. Let's say you have a school. Let's say this is the school. I know it looks like a house, so I'm going to add some other buildings here. Let's say this is a school. Cool. This school has 15 students who like basketball. Okay, basketball, pretty popular. It has 24 students. Actually, not 24. Let's say just 9 students. 9 students who like baseball. Baseball, I'm pretty sure you maybe have not heard of it, but it is a sport. It's a baseball. And 16 of them are interested in football. Okay, I'm pretty sure you guys have heard about that. So let's say we want to ask a question. How many students are interested in both basketball and football? Now, I know this is not enough information, but if we're given enough information, how I would do this is draw a Venn diagram. For example, this is a Venn diagram. So basically, let's say this is the set that represents all baseball players, okay? How many are here? There is 9. 9 here. But we don't write 9 because this region is actually this region. That region. Not this. This should not be included for. Which means we don't know how many like only baseball, okay? We don't know that. So now, time to learn another operation here. So let's say this is the people that like football. Okay, so this is the people who like only baseball, but no football, okay? Now, this would be represented. Let's say this set is B, this set is A, and this set is F. So this is set B, this is set F. We would represent this area, this just not this part, not this area with B/A, like this. No, not B/A, B/F. So B/F. B/F equals X, where X does belong in B, but does not belong to F. Okay, this is the definition. Okay, so here it's just B/F. I'm just going to write that. Okay, here it's F/B. People like football here, but not baseball. Here though, this region is people who like both football and baseball. So let's say that's, that will be F upside down U, B. F upside down U, B. So basically, I'm going to just cut this out. Yeah. It can be written as either F intersection B. Yes, this symbol is called intersection, or it can be written as B intersection F. So F intersection B, this equals set X. The set builder is the best method. So this is X, this is for all X such that X belongs to F and X belongs to B. Now, with this simple thing, these are all the regions, but I want to discuss more. Now, this. So now, this is A, this is B, this is F. Now, this section right here, only football, no baseball, and no basketball. So this section right here, how would we represent this section? Well, first, we will represent it as F/B. So only football, no baseball. But that is this whole region. That includes this region right here. So we would have to put this in parentheses and then do /A. So no basketball. And this represents this entire region. This region is also pretty simple. It's B/F. So no football, but it still includes this region. So this entire thing in parentheses, no basketball. So cool. This region, basically the same thing. We can do A/B or F. We can also do F/A or B, B/F or A. That does not matter. We can switch these two anytime. But I'm going to write F here. So F and then /B. So this means only basketball, no football, but that still includes this region. So to get rid of that, we do this. Now, this region is B intersection A. Simple, except that would include this region, because this is also a part of B intersection A. See, they intersect here, right? But there is F here also, so we will have to take this to the parentheses and then do F here. So now this will be written as, A intersection F. But that includes this middle region again. So we do /B. This region right here, in between these, this is basically the same thing, B intersection F. And then we have to do, /A. And now the final middle region. This includes all of the other regions. So this is B intersection F intersection A. We can put parentheses right here.
Okay, so আমরা যদি এইটাকে এইভাবে লিখি তাহলে লেখা যায় কিনা এটাকে সেটা হচ্ছে আমি যদি লিখি B
intersection A
তারপরে
/F
B
what
intersection F intersection
sir
A. এটা লেখা যাবে না?
Yeah, you could do that.
যেহেতু এখান থেকে এই পর্যন্ত এইটুকু হয়েছে আমাদের
You can also do that, yeah. But this intersection this and then excluding the entire region F, that does the same thing, right? Because because this region is the only region inside this thing that it has intersection with F. So that does the same thing. You can write that or that. It doesn't really matter.
ওকে, তো আমরা মোটামুটি আজকে এই পর্যন্ত ভেন চিত্র পর্যন্ত আলোচনা করলাম। তো তুমি জর্জ ক্যান্টরের যে একটা গল্প বলতে চেয়েছিলে, আসো এই সামনে দাঁড়িয়ে সেই গল্পটা একটু বলো তো, আমরা একটু সেট সম্পর্কিত জর্জ ক্যান্টরের যে গল্পটা সেটা একটু শুনতে চাই।
So, at around 1970s, 1960s, there was this mathematician called George Cantor. Not George Cantor, it's Georg Cantor. Yeah, so Georg Cantor was this like really famous mathematician who invented set theory, okay? So there were a few people were against this idea and few people were loving this idea. There was actually another thing that actually angered them. Okay, so here's how Cantor proved it. Cantor proved something else. So basically, let's take R. R is the set of all real numbers. So like decimals, fractions, everything you can imagine. Well, other than imaginary numbers. That's a topic for another day. Let's say we take all the real numbers from 0 to 1. So every single number you can imagine. Infinite of them. Now, we would represent this as uncountably infinite. Uncountably infinite. And uncountable infinity. Not uncountably infinity. Uncountable, yeah. All the natural numbers, if you don't know what the natural numbers are, they are just the positive integers. This is like, 1, 2, 3, 4, what you learned in school. This is countably infinite. Not countably, it's countable infinity. So, sorry. Okay, so why do we call these different infinities? That's because Georg Cantor proved this. So let's say we have a list. Now, we have already determined what equivalent means. Equivalent means when two sets have the same amount of elements. So let's say the amount of elements in all the natural numbers is equal to the amount of elements of the real numbers between 0 and 1. You should be able to do a one-to-one correspondence with that, right? This is proved by contradiction. So, let's say these are the naturals. And these numbers are the reals. Now, they're all from, 0 to 1. So, this is number 1. Let's just write a random, number here. Number 2. Let's write another random number. Because, you can't even start counting these. What's after 0? 0.0000. We would expect there to be a 1 at some point, but there is no 1 because it's infinitely long. So obviously we can't do that. So basically, what we do is we take the first number, we add 1. We take the first number, we will form a new number. 0 point. We will take the first decimal digit of the first number and then add 1. So 2 plus 1 is 3. We'll take the second decimal digit and add 1. We get 4. Then we continue this. Third decimal digit of third number, we get, and then add 1, we get 4. Fourth decimal digit of fourth number, add 1, we get 2. And then we continue on and on and on. This number will absolutely not be in this collection. We have an infinite number of numbers, but this number is nowhere to be found. Because, it's not the first number, the first digit is different. It's not the second number, second digit different. It's not the third digit is different. It's not the fourth digit is different. This number is never to be found in this entire infinite set. But, so when Georg Cantor proved this, some mathematicians, very happy, but some mathematicians were very angry at the fact that there can be infinities bigger than other infinities. Okay?
Okay.
But this is not the end. So then someone called Russell, this is a famous mathematician we're talking about. So this mathematician proved something. This mathematician proved set theory to basically be wrong, like the old set theory, like the set theory Cantor proved. Okay. So that proof is this. So let's say C. Actually, no, let's say S. Okay. So S. S is the set that contains every single other set that does not contain itself. So every single set that does not contain itself. This rule was not enforced in Cantor's old version. So let's say we have, the set of all even numbers, E. E is nowhere to be found inside E. The set of all naturals, N. Obviously, there is no set N inside N, right? So, yeah, ... But the problem is, look at it, S. This set, S is nowhere to be found. There is no S. Which means S does not contain itself. Which means S should be contained in the set that contains every single other set that does not contain itself, which is S. So S should be contained in S. There is no S inside S, which means S should be inside S. But wait, now S is a set that contains itself, which means S should not be in the set that contains every single other set that does not contain itself, which is S. Which means S cannot contain itself, but that means S should contain itself, but that means S cannot contain itself, but that means that S should contain itself. So we can never know. We don't know if there's an S in the set. But we should be able to see all the elements in the set, right? But we don't know. Like there can be S inside, there cannot be S inside. So if S is not inside, if S itself does not belong to S, then S does belong to S. But if S does belong to S, S does not belong to S, which is just a loop. Which means we have this back and forth loop, so we can never really know if S is inside S, which means S, it basically contradicts the entirety of set theory, okay? So, back to the story. So, after seeing this, letter that Cantor received by his friend Russell, Cantor was very sad. Some of the, people that were against set theory as a whole saw this as basically like, see, set theory is wrong. Saw this as proof as why set theory is wrong. But the other people that liked Cantor's idea said, we should just make a rule that does not allow a set to be contained in itself. Right? Okay. But the people that were against Cantor were like, what? This is just proving. This is just like changing the rules to a game so that you win. Like, right? Like a little brother changes the rules to a game so that you lose and stuff. Okay. So people were really angry at this. But eventually we did get around and said that for A to be a set, A cannot belong to A. This is a new rule in set theory. So yeah, that's the story.
Okay,
so goodbye everyone.